All right, today we're going to tackle a classic, how to figure out the volume of a sphere. Now, I know that might sound a little intimidating, but I promise by the end of this, you're going to see it's actually a surprisingly simple and really powerful idea. So let's start with a big question. I mean, a really big one. Have you ever looked up at the moon or thought about our own planet and wondered how much space is actually inside of it? Or, hey, what about a basketball? Or even a tiny little marble? That's the exact question we're going to answer today. So when we say volume, what are we really talking about? Well, for a sphere, it's just the total amount of three-dimensional space inside that perfectly round object. The easiest way to think about it is this. How much water could you pour inside of it until it's completely full? And we measure this in cubic units, like cubic inches or cubic meters. Now, to find that volume, we need a formula. But let's not think of it as some scary math equation. Let's call it a recipe. And just like any good recipe, it's just made up of a few key ingredients. You put them together in the right way, and you get your answer. So let's break this recipe down piece by piece. Our first and maybe most important ingredient is the radius. You'll usually see it written as just the letter R. All it is the distance from the dead center of the sphere straight out to any point on its surface. That's it. Getting this one measurement right is the absolute key first step. Next up, an ingredient you've probably met before, the one and only pi. Yep, that famous Greek letter. Pi is just a special constant number, about 3.1416, that magically shows up in pretty much any calculation involving circles and spheres. It's kind of the secret sauce. And the last piece of our recipe is a simple little fraction, 4/3. This number is what makes the whole calculation specific to a sphere's volume. Now, you don't have to worry about where it comes from right now. Just know that it's a fixed part of the recipe every single time. So, let's put all those ingredients together on the counter. Here's our recipe. The volume equals 4/3 times pi times the radius to the power of 3 or cubed. See? Now that we know what each part is, the formula doesn't look quite so intimidating anymore, right? Knowing the recipe is one thing, but now it's time to actually get cooking. Let's take what we've learned and use it in a real example. You'll see just how straightforward this whole process really is. Okay, let's pretend we have a sphere, and its radius is 5 centimeters. First things first, we write down our formula. Next, we just plug in that 5 where the R for radius goes. Now for the most important calculation, we need to cube the radius. That's just 5 times 5 times 5, which gives us 125. Finally, we take that 125 and multiply it by pi, and then by our fraction, 4/3. And bam, there's our answer. The volume of our sphere is right around 523.6 cubic centimeters. See? A nice, clean, satisfying answer straight from our formula. But hold on. What if you don't know the radius? That's a great question. What if the only thing you have is the diameter, the distance all the way across the middle? Or what if you just know the circumference, the measurement all the way around? Well, don't worry, there are easy ways to handle that too. This shows us that there are basically 3 different roads that all lead to the same place. We already know the main highway, using the radius. But if you start with the diameter, that's super easy. You just cut it in half to get the radius. And if you only know the distance around the outside, the circumference, there's even a special formula for that. It looks a little more complex, but it gets you to the exact same answer. And this right here is where it gets really interesting. Because the radius is cubed in that formula, the relationship between the size and the volume isn't what you'd expect. It's exponential. This means if you double the radius of a sphere, the volume doesn't just double, it multiplies by 8. It gets 8 times bigger. That's the power of cubing. A small change on the outside creates a huge change on the inside. So why does this matter? Well, this is way more than just a problem in a math book. Knowing how to calculate a sphere's volume is incredibly useful out there in the real world, for everything from designing a soccer ball to trying to understand the cosmos. You really do see this everywhere. Engineers have to use it to figure out how much can fit inside those giant spherical storage tanks. Astronomers use it to estimate the sheer volume of planets and stars. And designers depend on it for, well, everything from sports equipment to tiny, perfect ball bearings. It really is a fundamental calculation. Now, before we finish up, there's one really common mix-up that I want to clear up for good. People often get a sphere's volume confused with its surface area. They sound kind of similar, I know, but they measure 2 completely different things. Here's the simplest way to think about it. Volume is the 3D space inside the sphere, its capacity. Think, how much can it hold? Surface area, on the other hand, is the 2D space covering the outside of the sphere. Think, how much paint would I need to cover it? So inside versus outside. And of course, since they're different things, they have different formulas. So what makes all of this work so beautifully? It really comes back to the simple, perfect nature of a sphere itself. Every single point on its surface is the exact same distance from its center. It's that perfect geometric symmetry that allows us to use such a consistent and powerful formula. So, I'll leave you with this final thought to chew on. Now that you know that a sphere's volume grows by the cube of its radius, that it takes this exponential leap, how differently do you see the small and large spheres all around you? From a tiny pea to the moon up in the sky, that inner space, their capacity, is so much more dramatic than you might have ever imagined.